So now what I would like to do is to discuss something which is slightly more technical so that we can link to the tutorials and have a feel of what's going on into these input and output files, okay? I guess the point that what we want to discuss really is what is the meaning of this cutoff energy that we have the input file. So that has to do with something called Planewaves. And what is this mysterious pseudopotential that we mentioned yesterday. So I guess the bottom line of the entire discussion about DFT is that what one needs to solve is Schrödinger's equations, okay? The complexity is that, as we see in the previous lecture, so one solves the Schrödinger equation, then gets a density, and then loops through until everything is so converged, right? So it's one has to solve this kind of equation many times, all right? So at this point, this is a, we've seen that for the hydrogen atom, the structure is very similar, but we are used to do things by hand for the, when we are undergrads on these things. So there is no way to do this by hand if you're dealing with real materials. So one has to find, numerical strategies to solve this problem. So here we're going to discuss some of the strategies. And so the first observation is the following. So this, if you think about it, now let's forget DFT and everything else. That's essentially a differential equation. And it's in particular is a second order partial differential equation. Okay? So there is a del square here. So second order equation means that you need two boundary conditions. But this is a second order PDE in 3 dimensions. So that means, for instance, if you take the variable x, okay, so if you have x, y, and z in the reference frame, well, you fix y and z, and for each value, each pair of those, you need 2 boundary conditions for x. So let's consider a simple case, which is an isolated system, like an atom or a molecule. So the natural thing to do is to say that if you take a molecule, somewhere, very far away, the electron, the probability of finding electron is 0, right? So that you have the electrons on your molecule. So one uses in this case is something called basically boundary conditions are at infinity. That means that once you choose y and z, you say that if x is equal infinity, or x is equal minus infinity, in this case I put 0, basically the wave function vanishes. Okay? So these are 2 conditions that you can use in order to completely define the solutions of this partial differential equation. So that's a possibility. So this choice is used typically in quantum chemistry codes. So if you have seen Gaussian, that's basically the boundary condition which is enforced. Okay? So in what we are doing this week, we are using codes which are designed for solid state calculations mostly, materials, nanostructures, but can also be used for molecules and things like that. But they are mostly designed for extended systems, okay? Maybe interfaces, but bulk systems. So in this case, clearly you cannot use the values at infinity because the system essentially is infinitely extended. It's everywhere, okay, mathematically. So what people use is something called periodic Born-von Karman boundary conditions. That means you consider a box, okay, and you say that your wave function, when you reach this point, is equal to the value at the other end, okay? So that's just another possibility. That's actually something that works very well, and clearly it is not exact, but you can imagine if the size of the box increases, you make it more and more exact in principle. So using that, you have 2 conditions. One, that the wave function is identical when you go to the end of the box. So basically, so if that is your simulation box, you're saying that the value of the wave function here is identical to the value here. So that's the first condition. The second one is that the gradient of the wave function is also the same. Okay? So the fact that one imposes a continuous wave function and a continuous first derivative have to do with basically continuity. And so one can show that this has to do with essentially a conservation of the number of electrons. So these are basically the 2 conditions that one uses. So if you use those 2, and this second order PD, everything is well defined. So the problem at this point can be solved mathematically. There are solutions and one can find them. So how do people go about finding solutions? So first of all, let me say something more about the Boromon-Kalman conditions. What you see here basically is an example of a amorphous solid. So this is a ball and stick model of vitreous silica, okay, SiO2. So that's basically what you see in the window down there. So that's precisely that. Okay. So what I'm showing you here basically is that if you look at that, it seems completely disordered. But actually, for instance, if you follow this bit, you will see that this is identical. So this is identical. Is identical. So these 4 boxes are a repetition, periodic repetition of this one. So what we would do in a calculation is to specify the atomic coordinates of these atoms here in this box. And the code essentially works with these atoms, but in practice, the Schrödinger equation assumes boundary conditions where this is repeated periodically up to infinity. Okay? So that's a very standard thing to do for solids. And the only surprising thing is that when you want to study a molecule, you can still do it, but still you don't have one isolated molecule in this kind of software. So if you have a water molecule, for instance, you put the water molecule at the origin of the reference frame, what you are really simulating is a water molecule at basically at the corners of a cube which defines your simulation box. Okay? So that's what one is really calculating. This is not a problem because if you are careful enough and you use a large box, so these molecules will not interfere with each other. So if the wave functions do not overlap, you are fine. So typically what one does, if you want to study a finite system like a molecule or an atom, you place this in a box, you choose a size, which is, I don't know, maybe a few times the linear size of the molecule. You perform a calculation, you look at the property you want, and then you double the size of the box, you calculate it again. If the property has not changed enough or much, then you're fine. If things are very sensitive to the size of the box, then, well, you need to converge it. So you need to use a box which is big enough to avoid any spurious effects. But basically, that's the way to imagine calculations. Everything is repeated periodically. Okay. So now, how does one deal with that? What people do is not what I showed you yesterday about partitioning space in points and then recording the value of the function at each point. So that is possible, but it's not very popular. Okay. So you don't write down the wave function at each point and do operations with this object. So people do something which is actually a bit more elegant, and that is essentially a simple Fourier transform. So what they do, so suppose we have a wave function in one dimension. What happens is that you write down your wave function as a Fourier series. So you have coefficients times exponential to the I 2 pi n x over a, where n is an integer running from minus infinity to plus infinity. Okay, so that's something that you must know from, I don't know, first year undergrad maths. Okay, so that's just a Fourier transform of a function. There is not really complicated. So clearly, if you represent your wave function in this way, you don't want to record the values at each point. What you need to record on a file is just the coefficient of each plane wave. So that's what is done. Let's just take a look at these things. I mean, obviously this is completely trivial, so forgive me if it's too stupid. But so this is essentially a complex exponential. The real part would be a cosine function, so something like that, the blue line, and the imaginary part is a sine function. So there is really nothing complicated. So completely trivial. So now, the reason why this is useful, so the first reason, is that if you look at these functions, okay, if I replace x by x plus, let's say a, the size of the box, okay, so that is going to basically become exponential I 2 pi n, okay, times this object. But exponential I 2 pi n is 1. Okay? So in practice, if I translate this object by a lattice constant, I get the same object. So the first boundary condition is already satisfied. So whenever I express this as a linear combination of these objects. Then the second boundary condition on the gradient is also satisfied. You can check that in 2 seconds, by hand. So in practice, what I'm trying to say is that if you represent the wave function as a linear combination of these complex exponentials, okay, all the two boundary conditions are automatically satisfied, so you don't need to worry about that. So these complex exponentials are called plane waves because it's basically they describe the propagation of a monochromatic wavefront. Okay, so that's in one dimension. So that's basically what is done in what we call plane waves codes. Okay, which is the example is the one that you're using now these days. Well, that was the 1D case, which is clearly the simplest. Situation gets slightly more complex when you are in 3D, but it's really just a matter of bookkeeping. There is no new concept of no difficulty. So in the case of 3D, you need to go back to your solid state physics books. And there, if you remember, people talk about something called, well, the lattice vectors. Well, you know better than I do what is a lattice vector. But from that, you can construct the reciprocal lattice vectors, okay? So if you have, for instance, A1, A2, and A3, so the three lattice vectors, you can always construct the dual lattice, which is basically the primitive cell of the reciprocal lattice. The recipe, for instance, for B1 would be this one, okay? I will not spend time on that because this is really something that it's second year undergrad. So for experimentalist theories for everybody. Once you have those, you can construct all the vectors of the reciprocal lattice by taking integer multiples of these primitive vectors. Okay? So this is an example. If you take graphene, you have only two lattice vectors in 2D, so A1 and A2. So you define the unit cell. By replicating that, you get the entire lattice. If you use this recipe, basically, you generate B1 and B2. Those is the reciprocal lattice, and then you can generate all the reciprocal lattice points this way. So these points on the reciprocal lattice are typically called G vectors. Don't ask me why they are called like that. Okay. So in the code, so in the output of the code, you will see like a number of G vectors or things like that. Okay. So that refers to how many of those you have. And then, just to say, we had in the case of 1D, we had something like exponential I 2 pi n x over a. So that was a plane wave. So this is 1D. In the case of 3D, the situation is slightly more complex. It's something like that. So you have just a scalar product between the G vector and the position where you are. Clearly, this is two vectors. Scalar product is a number. So that's all well defined. Okay? So that's a plane wave in 3 dimensions. So in practice, what happens is that in all plane wave codes, the electron wave functions are expressed as a linear combinations of plane waves. Okay? What we store, what we try to calculate, are the plane wave coefficients. Okay? So it's basically the coefficient define this linear combination. So that's basically a choice of representation. And in the technical jargon, this thing, so the set of these plane waves is called a basis. Okay? So you expand the wave function into a basis. So this is for typical solid state physics codes. If you do quantum chemistry, this is not what is done. What people do is to use an expansion in terms of atomic orbitals. That's another choice. Okay? So it's a different kind of language, different properties, but it's just a way of avoiding recording the wave function at each point, but just recording the coefficients in some kind of basis. In this case, the basis are plane wave basis. So that's it. So why I'm talking about that? Well, basically the question is, so this in 1D in principle should go from minus infinity to plus infinity in all, in 1D. In 3D, it should go from minus infinity to plus infinity in every direction. Okay. So in principle, that means I would have to store, an infinity of coefficients, which is clearly not practical. Okay. So one has to make a choice there and see, which ones or how many do I pick. So to see how many I can pick, let's basically reconsider the same Schrödinger equation we had before, okay? But replace this expression inside the equation that we had at the beginning. So if I go back a second, so if I place that expansion here, then here, and then here, okay, I find an expression where now we got rid of the space variable, and we replace that with the basically the plane waves, so the G vectors. Okay, so we don't have R anymore. Everything is expressed in terms of G. So that's basically a representation of the Schrödinger equation we want to solve in terms of G vectors. Now, let me just mention, in order to be more accurate, that this is not the way a code operates. Okay. So this part is done precisely in this way, the kinetic energy in any plane wave codes. This is just a formal expression, and things are not like that in a code. Okay, that would be way too slow. So what is done here is a trick where one does it in real space and uses fast Fourier transforms back and forth to be very fast. Okay, so in order to do this in practice, one has to use modules like the one we had to load yesterday, like a module load FFTW3, things like that. Okay, so that is to deal switching between real space and reciprocal space at this point to make the calculations much faster. But the point is that, as you can see here, is that whenever you have a certain plane wave, actually that defines a kinetic energy, which is G squared over 2. Okay? So how many plane waves do I need? Let's see what it means to have a high, basically a large number here. If I have, I'm looking at one dimension, the modulus, for instance, in this case, will be 2 pi over a. So I have this kind of wave. If I double it, okay, I double the period. So what happens is, so I half the period, sorry. So I have something which goes basically as 2 wavelengths. If I triple it, there are 3 wavelengths. So what you can guess is that as I increase this number, as I go higher, this becomes finer and finer. So I can describe the space in a finer and finer way, okay? So the idea is that the higher I go, the finer the description of the wave function I can achieve. Okay, so in principle, I would like to have something very, very large. So a standard metric, so since you see that here, this depends on the lattice parameter. So if you're using a system with a slightly larger lattice parameter, it gets confusing because, what do? Do you count the number of plane waves, or you count the largest plane wave? It gets a bit messy. So what people use as a criterion is the kinetic energy corresponding to a given plane wave. Okay, so they say I stop the expansion here, okay, by setting the highest energy corresponding to this number. So what people introduce is basically the equivalent energy of the largest G vector you have. So if you take G squared divided by 2, that's a kinetic energy in Hartree units. And what you get there is a single parameter which tells you what is the largest G vector you incorporate in your expansion. Okay? Clearly, the larger this number, the more accurate the calculation. So this is what in the tutorials you've seen is called like E cut WFC, something like that. So it's the cutoff of the wave function. Okay. So what that means that when you did yesterday, or you will try today to do the convergence of the total energy with respect to this cutoff, what you're doing really is to incorporate more terms into this expansion. Okay. So ideally, one wants a mathematically exact expression where you have all the terms in the expansion, but that is numerically impossible. You may be there running calculations for years. But really what you want, suppose you calculate the total energy, for most applications, if you have a 3-4 digits accuracy, that's more than enough, okay? So if you achieve a cutoff, suppose 20 or 30 Rydbergs in this number, which gives you a number which is converged to 4 digits, you don't need to go beyond that, okay? Because you already achieved your kind of accuracy criterion. So in principle, if you include all the plane waves, you will get accuracy to infinite number of digits, but you don't need that, okay? So also because a computer is typically maybe double precision now, so beyond 16 digits, nothing goes. So there is no point of pushing this too high. That's one point. The other point is that we need to always perform a convergence test on that, okay? So that's absolutely critical, because if you use a cutoff which is not good enough for your system, you're just trying to solve this kind of Kohn-Sham equations of DFT by using a very lousy representation, and you're going to get some just garbage. Okay? So the tests of convergence on the cutoff are absolutely critical and have to be done all the time. Okay? Now the bad news is that, so the good news is that this cutoff, once you decide it for a given pseudopotential, let's say, that's typically quite a good number. You can keep it throughout your calculations. But if you're doing something a bit more refined, you will have to check this number for each kind of property you want to calculate. So if you achieve a convergence, let's say at 30 Rydberg for a total energy, it might be that when you go calculating, I don't know, vibrational frequencies, there's not going to be enough. So maybe your error is going to be 5%. You don't want that. So you will have to go to 60 Rydberg. Okay? So for each property, the idea is that you repeat the calculation until the number you get is stable. It doesn't depend on this anymore. So ideally, you need to be at convergence all the time. So that's basically one thing I wanted to say. So that's the second bit. That's the name we introduced yesterday, the pseudopotential. Okay? So that's something that you will see everywhere throughout this week. The idea is actually very, very simple, and it's not unique to DFT. It's something which was around since the beginning of quantum mechanics. So what you see here basically is just a colorful way of representing a few numbers, which are the eigenstates of the silicon atom. Okay, so just one atom alone, and this has been calculated using DFT and the local density approximation. Okay, so I did this calculation just to look at the eigenvalues. And just as a reminder, silicon is here. So you have basically 1 electron here, 1 electron here, 2 here, 6 here, and 2 and 2. So this is called the core electrons, and this is called the valence electrons. Why is that? If you look at the eigenvalues, so the 1s level, so this guy here, it's minus 2,000 electron volts with respect to vacuum. So it's really, really deep. Now, if you go higher up, you go to the 2s. So the 2s is here, is minus 140 electron volts. Okay. So if you go to the 2p, so this other thing is minus 96. Okay. So it's very, very low. Only when you go to basically the 3s and the 3p, you have basically eigenvalues which are a minus 11 and minus 4. So when you try to make things with this atom, and it bonds with other atoms, I don't know, you oxidize it or it forms a crystal. So only these states will be involved because these are the ones with energy closest to vacuum. Okay, so the next state is 100 eV below. It's not going to do anything at all. Okay, so that's as simple as that.
Are you able to use those atomic states, or do you have to consider the fact it would be hybridized in a real silicon crystal?
What you mean?
The 2 electrons
Yeah.
in the 3s
Yeah.
and the 3p
Yes.
will form hybrid
Yes,
states,
correct.
of course.
Yeah.
And those are 2 atomic state energies that
Yeah.
I see
Yeah, yeah, yeah.
there.
Yeah, yeah.
Hybridization, can you just do this with atomic orbitals is what I'm saying.
Yeah, so basically this is just a way to figure out the order of magnitude of these energies for the atom. If you look at a crystal, so these energies will change. One has to do calculations for the crystal, and they will be widely different. If you go silicon oxide or silicon crystal or silicon nanowires, you can actually, this can be a starting guess, but the final numbers will not be those ones. But happens actually is that what people consider is that will most likely not change, that will not change, that will not change. So if that is the case, we can get rid of all of this, so the blue ones altogether, and not consider them. So there is a practical reason for doing that. So if you are in silicon, okay, it's 28, silicon is 14, you have 14 electrons to deal with, okay? Okay, you could put all of them, although there are problems I'm going to discuss in the next slide. But if you are down to lead, you might have, I don't know, 200 electrons or something like that. So, it's, the calculation time is going to go up quite dramatically. So just to give you an idea, yesterday, for those who managed to get to the last exercise of the tutorial, essentially, if you didn't do it, try to do it today because it's interesting. Essentially, what I did is to put input files for pieces of silicon, okay, with increasing number of atoms in the unit cell. And I asked, basically in the question, I asked to plot the time needed to perform a calculation as a function of the number of atoms. So what you see by doing the tutorial is that the time needed scales with essentially the cube of the number of atoms, or more precisely, with the cube of the number of electrons. Okay, so that means that if you double your number of electrons, the calculation takes 8 times longer. So yeah, for silicon, we're doing things of a few minutes, maybe 10 minutes. But if you do a real system, maybe an interface, and the calculation lasts maybe 4 weeks, going 8 times larger, it's something which starts to be not only time consuming, but also, financially expensive, very expensive. Because, calculation time on machines is not something that comes for free. You have to pay for it. So the idea of getting rid of core electrons if they're not needed is very important practically. So now, let's just see how these core electrons look like. I'm going to go on this side. So what you see here basically is the DFT LDA electron, maybe I'm going to be like this, electron wave functions in silicon. So the 1s, okay, is this black line. So you see it's nodeless and it's very, very localized around the nucleus. So if you go to the 2s, the situation gets slightly more complicated because now you have one node. So this black line intercepts 0 here. So there is one node. So that's typical. Whenever you go higher in the principal quantum number, okay, you start introducing nodes, so zeros, in your wave function. So if you look at the 3s now, in fact, you have two nodes, one here and one here, okay? And it becomes more and more delocalized. If you go to the 2p wave function, what you see is that the 2p has no nodes here, because it is the first function of the angular momentum p. And if you go to the 3p, it acquires one node that you see here, basically, okay? So the interesting bit here is that all the 1s, 2s, and 2p functions are very much localized near the nucleus, and the 3s and the 3p are very much delocalized, okay, far away from the nucleus. So to give you a better idea of what is going on here, what I'm plotting, instead of the wave function, I'm plotting the square modulus of the wave function, so the probability, the density, and I'm adding up all the core electron, basically densities, and all the valence electron densities. So this is the core density. So this is the valence density. As a measure, as a reference, I'm putting here the distance between two silicon atoms in a silicon crystal. Okay? So that means you have to imagine one silicon atom here, one here. So this is pretty much the middle of the bond. So what is happening is that the valence electrons are all packed in the middle of the bond. So this will be the responsible for forming bonding in this structure. The core electrons have a bit of overlap here, but mostly they are located in this region. So clearly you can imagine that if you have the same core electrons on the other side, if there is another silicon atom, the two core groups, they will not overlap with each other. So we don't need to care too much about that. Okay? So that's the principle for partitioning the electron density into a core electron density and to a valence electron density. And what people do at this point is to try to embed the core electrons into the nuclear potential. So you assume that they are completely frozen, they stay with the nuclear potential and then will never change. Okay, that's called the frozen core approximation. So if you do that, you are modifying basically the nuclear potential, and that becomes, since it contains electrons which depend on the atom, that becomes a nuclear pseudopotential. Okay, actually it is called an ionic pseudopotential because now in silicon the charge should be 14, but if I incorporate 8 of the core electrons in the nucleus, let's say, the actual ionic charge will be +4. Okay, so that's why we talk about ionic pseudopotentials, because now we're not longer talking about nuclei, but we're talking about ions. All right. So what happens at this point? Let's go. So that's basically a way to reduce the number of electrons. Okay. So to use a bit less electrons, so we can go faster. Now let's see what happens from the point of view of describing the wave function. There is another advantage in doing this operation, and that's the following. I told you that if you look at the silicon 3s wave function, since it's the level 3 in terms of principal quantum number, we will have two nodes, one here and one here, okay? So nodes are something which is very bad in the sense of numerical precision, because you need, in order to describe these fluctuations, you need a lot of precision. So you need, so imagine define a grid to capture these fluctuations here. You will need a grid which is very, very, very fine here, okay? So you need a lot of points. So let's now assume that we use something like a spacing of the order of, I don't know, this is maybe 1 Bohr to describe your wave functions. Okay, that's just an example. So the way the numerical code we would see this wave function if we use a spacing of 1 Bohr, we basically a point here, one here, one here, one here, one here. So here we miss a bit this kind of peak, then 1 point here, one here. So we are cutting through the nodes. So we are messing up the wave function. Okay. So that's really not a good thing. So in terms of plane wave cutoff, that means that in order to describe these things, you may need a kinetic energy cutoff, which is of the order maybe of 100 Rydberg or 200 Rydberg or 300. So the calculation becomes very, very, very time consuming. So what people invented, and that's quite actually one of the really enabling technologies of the whole DFT operation actually. So it's really, really, probably is what really enabled material science using these calculations. Is a very smart trick which goes as follows. So you have these nodes here, and what I told you is that most of the physics, like the action, happens in this region, okay, which is not near the core. So some people got smart and say, okay, but then why do we need really to be accurate on this side? So what do we care if this is not active, chemical, in terms of formation of bonds and things like that? So what we really need is to be absolutely accurate on this side, okay? Let's say in the valence region. Maybe we can be a bit more lousy on this side. So this clearly is an approximation, but what people had as an idea is the following, which is pretty smart. So instead of having a wave function which has two nodes, okay, let's cut through. So let's design. So let's design a new wave function which is identical to my original function here. When I get to this point, instead of following these fluctuations, which are very expensive, I just cut through. I go smoothly to 0 without any nodes, okay? And here I use some kind of polynomial which is very smooth and which can be described accurately using a very small plane wave cutoff, okay? So that's called, this operation is called pseudization. That means I solve, really I perform a numerical solution of the wave functions. So that's basically that. So that's the first step in the generation of pseudopotential. I generate my wave functions here. And at this point, I'm not happy with these nodes. So what I'm going to do is to take the wave function, cut through, and define new wave functions, okay? So one says, okay, what do I do with that? This is going to be dependent. If I put it into a material, how do I use that? So that's the trick. And I mean, it's a bit technical, but I think it's quite spectacular. So I want to mention that. So people say, I really would like the wave function to be like that, even if I lose a bit of information here. So how do I do that? Because the solution is not that. The solution is this one. Well, people say, well, what we can do is to invent a new potential, actually, which gives me the red line as a solution. As simple as that. So how do you do that? Well, you can use the Schrödinger equation. So if I now generate a new modified wave function, the red one, I can plug it into a Schrödinger equation, okay? But this time, I know the wave function. I know the eigenvalue because I did a calculation before. What is missing is the potential which generates this function. So what people do basically is to say, I rewrite this equation by trying to solve for the potential this time. So they determine a new potential which is obtained from the wave function and from the eigenvalues. And that's what is called a pseudopotential, okay? So this is essentially a way to say, I don't like this function here. I would like to work with something smoother, which is easier to describe from the numerical point of view. So I actually chop the function here. I cut through with something smooth. And now I ask myself, what is the potential which generates this red line? And the answer is obtained by inverting this equation and looking for the potential which gives that function. So that's called pseudization. So this is something which is done. You don't need to worry about that. So when we seen through this table of pseudopotentials yesterday, all of those, somebody else has done this operation for you, basically. This has been tabulated, these have been tested, these have been developed and maintained, and published in papers. People record which papers have been used, so in which papers these are being used. So there is a lot of literature on that. But that's basically the procedure. And just to give you a flavor of how it looks like, so in the case of silicon, that would be the ionic potentials minus 4. So we have 4 plus ion now. That would be minus 4 divided by R. That's the pure potential in silicon. So the way this operation goes is to redefine this potential in such a way to be identical to the original one up to a certain cutoff. So that's where we are chopping the wave function. And then it's modified in order to give us the red line that we had before. So this is really the potential that the code sees when you load a pseudopotential for your system, okay? So when you use this instead of the black line, in practice what you're doing, instead of having nodes, you find this red line here. So it's a bit a smoother function, okay? And this is not problematic for most applications because, again, this region is not the one which participates in bonding, okay? So that's basically the idea. So what we called pseudopotential yesterday, which we download and we use, that's precisely something which replaces the pure ionic nuclear potential by something which has been modified, okay? So this operation actually is absolutely critical because, so what you can try as an exercise if you want today, try to do, so any of the examples you did, okay, crank up, so you use maybe a cutoff of 25 Rydbergs, try to do the same calculation and put 500 Rydbergs there. you'll see how long you're going to wait. Okay? And to do those nodes, you will need something of that order, because that's basically atomic physics. Okay? So the use of pseudopotential is what really enables computational material science, studying many atoms. So that's really, really critical. Now let me give you the last bit of information, and then we close. That's basically the last slide. So yesterday you seen another parameter, which is basically was called K points, and that was for the case of solids. There is nothing really complicated about that. So if you remember, the book of Kittel or Ashcroft and Mermin, you will remember the block theorem. Okay, that theorem tells us that in solids, any wave function can be expressed as the product of a plane wave, okay, times something which is periodic in the unit cell. Okay, as simple as that. So there is nothing new. This has nothing to do with DFT. This is something standard solid-state physics. Okay, but clearly DFT, has to take into account solid-state physics, not something different. So when we take this into account, the density that we've written like that, sum of the square moduli, here I just use a discrete index. In practice, okay, maybe since you guys are struggling from this side, in practice, what we can do in the case of solids is to rewrite this wave function using this expression, so the block form of the wave function. And what is going to happen is that each wave function will basically acquire an index which is the block momentum. Okay? So this is what is called the K point of the wave function. And instead of having a discrete sum, we need to sum, so basically to integrate over the Brillouin zone of the material, and that's a continuous integral, okay? Clearly, we don't do continuous integrals in a numerical software. We discretize that using a set of points. So we will have to sample the wave functions at discrete K points in the Brillouin zone. So to give you an idea, so this is the Brillouin zone of silicon. FCC crystal, you've seen this a million times. When you say, when you use this keyword, and you set something like, 444000, that simply means so take this, slice it with an array of 4 by 4 by 4 points. That's the way we represent in a discrete way, the Brillouin zone, okay? So that is something which is not important if you do molecules or things like that, but it's very important if you do a crystal, okay? Because you need to represent, to take into account the block theorem when you do these calculations. And also this is a convergence parameter, so the total energy will depend on how many points you put in there. So you need to make sure that you have enough that your energy is stable, is not changing anymore. I think this is the end of this lecture, and this afternoon, basically, what we're going to try to do is something a bit more advanced than yesterday. We want to try to calculate the binding energy of the chlorine molecule, the cohesive energy of silicon, and then you will have to try later to do to look at something completely crazy, which was requested by your organizers, the binding energy of graphite, which is much more complicated. So that's basically the end of the story today. And that is going to be very interesting because you will see the problems of DFT when we look at layer materials. Okay?
I want to ask about the pseudopotentials.
Yeah.
So we saw there was a whole list of pseudopotentials yesterday.
Yes.
Is it because they have a different cutoff, or what's
Yeah, okay. So there are two things. Let's go here. So so typically in that list, there are two kind of labels. So in the case of silicon, there was something like silicon PZ PBC dot, I don't know what was the name, UPF, okay, so something like that. So typically this label is the flavor of the exchanging correlation in DFT, okay? So PZ is the Perdue-Zanger parametrization of the local density approximation, is the thing that we discussed earlier in the previous lecture, okay? So so here maybe I should stress that when you start to do a calculation, you choose your exchanging correlation. So everything in your system has to be consistent. So pseudopotentials all have to have the same. Otherwise, you're putting like peaches and apples together, okay? So that is the first label typically. I say it's a bit of a convention, but sometimes you also find something like, if people are not careful, something like that, and you don't know what it is. So you have to go inside the file and see. So in the header of the file, you will see exactly what that is. But typically, this means the exchanging correlation. This, in this case, is von Barth and Carr, is a recipe which was proposed to actually generate the pseudopotential. So how recipes can differ? It's actually quite simple. So all pseudopotentials make sure that actually everything on this side, beyond this cutoff, is identical to the all electron calculation without the pseudopotential, okay? But clearly, here, the only thing you want to do is to remove the nodes and cut smoothly so that actually you can use a small cutoff at the end of the story. But you can imagine there are many recipes for doing that, okay? So there are many recipes, some early recipes, something smarter, something that, for instance, some people, what they did is to say, I want to have a polynomial here with some constraints. How do they determine the coefficients? So you can optimize the coefficients so that the cutoff at the end will be the smallest possible. So there is a lot of technology to find this bit. So the second label actually is something which labels the technology used to generate this kind of thing.